Hello and welcome to the presentation of ICCIT 2023 26th International Conference on Computer and Information Technology. Welcome everyone. Today I am presenting my paper ID number is 924, Design and Finite Element Analysis of a Single Mode Modified Circular Microstructured Optical Fiber for High Negative Dispersion and High Nonlinearity across E to L communication bands. Myself, Amit Haldar, currently serving as an assistant professor at World University of Bangladesh, and here are my authors: Mohammad Shami Anwar, Wahiduzzaman Imon, Riyad Tanshen, and Mohammad Sharifuddin Sujib. Here is the introduction of my presentation. As we know, the rapid expansion of optical communication networks demands innovative solutions to combat dispersion challenges. So, the dispersion, where different light wavelengths move at varying speeds, hampers signal integrity and data transmission. And we need to make a solution to it. So, photonic crystal fibers offer unique structural features and band gaps controlled light propagation, revolutionizing optical fiber design. And our focus area is to enhance V parameter, high nonlinearity, and modified critical parameters ensure high speed, high quality optical communication networks. Here is the picture of the optical fiber or the microstructure optical fiber, which is known as photonic crystal fibers. So what is actually a photonic crystal fiber is? So the photonic crystal fibers are advanced optical fibers designed with periodic microstructures enabling precise control over light propagation. PCFs address dispersion challenges, ensuring high quality signal transmission in the face of increasing data rates and longer transmission lengths. Periodic microstructures, air holes, or high index materials arranged in a controlled pattern. Band gap engineering is also an important part. That is a selective transmission of light wavelengths offering tailored dispersion characteristics. So here you can see there are the two optical waveguides, that is known as the PCFs. So the purpose of the PCFs play a pivotal role in preserving signal integrity, preventing data loss, and enabling high-speed, reliable optical communication networks. So our future focus is ongoing research aims to enhance PCFs birefringence, nonlinearity, and critical parameters, promising even more efficient and advanced optical communication solutions. So these are our objectives: to design simple modified circular lattice microstructured optical fiber, to analyze numerical aperture, to analyze single mode operation, to enhance the nonlinearity, dispersion compensation for wavelength division multiplication communication, to reduce the confinement loss. Now this is the methodology of our research, that is to get realization of proposed MCMOF waveguide which will achieve the objectives, design what waveguide by using finite element method based software, and investigate the characteristics by using console multiphysics, and plot the data by using high level programming language software. Now here we use two tools for this research, that is the console multiphysics software, and other one is MATLAB software environment. So these are the required mathematical formula that we have used to analyze the optical properties of the photonic crystal fibers, and that is our basic modified circular microstructured optical fiber MCMI design. That is the proposed design that we have designed here. So here is the composition of circular cladding with 4 air hole rings, as you can see here, and each of the air hole has different relative air hole diameters, and the whole modified circular microstructured optical fiber has a pitch of 0.9 micrometer, which is the lattice structure. And achieving a modified circular configuration, we have used such material with fused silica. Perfectly matched layer boundary conditions are there. Our purpose is to prevent reflections, simulate infinite domains, and minimize active artifacts. And we kept our PML thickness to 10% of cladding radius. Now the main theme of this modified circular microstructure optical fiber designs. There are a lot of circular designs of PCFs in some literature reviews, but here in the circular cladding structure with varying air hole angles, there are different type of angles we have turned it on. As you can see that for the ring number 1, the diameter 1d1, that the spacing between the two air holes are 30 degree. For D2 it is kept 15 degree, D3 also kept 15 degree, but at D4 it has been kept for 17.5 degree. The benefits of the design methodology: it enhances the stability and accuracy in modeling, as we use the D4 as 7.5 micrometer, that enables us to make it more compatible for single mode operation, and it also enables detailed analysis of optical phenomena. So here is the chromatic dispersion that we have studied here. The dispersion values spanning from 3060 nanometer to 1625 nanometer are highly negative, reaching minus 564.3 picosecond per nanometer kilometer. And here you can see that is the 1.55 for the 1.55 micrometer we have achieved high negative dispersion, which is very much important, and the whole chromatic dispersion is highly negative in the 1.36 to 1.73 wavelength from the E to L wavelength band. That's the thing. Now we have also studied for the chromatic dispersion by changing the pitch value. When we change the pitch value with the plus minus 0.1 micrometer variations, we get some important facts. That is, when we just reduce the pitch value, we get the high negative dispersion. When we just increase the pitch value, we get the lesser negative dispersion. And by changing the air field fraction D3, there is a third air hole ring there, and that is, if we change it from 0.65 to 0.55 equivalent, so for this micrometer changes on the that is the change on the diameter of the air hole, the dispersion decreases from minus 655.7 to, and when we just increase our diameter, we get the, when we just decrease the value, the D3 divided by the pitch value, that is decrease 0.55, we get minus 768.4 picosecond per nanometer kilometer at the 1.55 wavelength, which is very high negative. And if we just increase the value at 0.65 from the optimum value, then we get the dispersion has been increasing. So that is gonna be the changes where we change the third air hole ring, but it seems to be all of the data are under the high negative dispersion range. So that's the important part to understand the single mode operation. To analyze the B effective, we have consistently remain we get the value consistently that remain 2.405, a condition necessary for single mode operation, and specifically at the 1.55 micrometer wavelength, the V parameter is calculated as 1.959. So confirming the fiber suitability as a single mode contender for optical transmission. So that is also a very good contender of a single mode operation as far as the B parameter concerns. Now the numerical aperture is also important. So here we analyze the wavelength dependent numerical aperture curve, and we get 0.5369. This is one of the basic thing, that when we get the higher numerical aperture, that allocates more light through to the whole fiber. Now this is the effective area and nonlinearity. So while analyzing the effective area and nonlinearity, the effective area is very much lower than comparatively some of the basic literature reviews that we have done before. That is, been get 1.888 micrometer square, and that achieved a high nonlinearity of 66.54 per watt per kilometer. That is the essence of understanding the effective area and nonlinearity. Both are relatively vice versa to each other. If we get lower effective area, we will get higher nonlinear coefficient. So that is the relationship between these two. And there is a confinement loss, and we have here measured the confinement loss within decibel per centimeter range, and for that we get 2.633 decibel per centimeter, which is comparatively a lower confinement loss according to the optical fiber communication. Now that is the EM field distribution, that's the electromagnetic field distribution, as you can see here, of the proposed MCMF, and the light has been coupled under the H11 conditions. Now there is the comparison with different MOFs design, it's microstate optical fiber design. We have studied several differences, and just while we just consider the several recent literature reviews, so there are some references. So from studying the recent advances of the optical fibers, we get high negative dispersion at 564.3, and this design is quite less complex than other designs, and we also get the effective area much lower comparative to the other designs, and also we achieve a high nonlinearity, 66.54. It is a relatively high nonlinearity that we have achieved, rather than reference 2 has get the high nonlinearity. So that is gonna be the very important part, that we have achieved a very good, relatively very good results. Not only good, that is comparatively the best results found in the matter of the effective area and numerical aperture parts. So that's going to be a very good tool. So these are the references that we have used here to just understand and just analyze our designs. The all of the references are very recent references that we have used here, and for that we get good result through the references. So thank you very much all for just listening to my presentation. Hopefully I am giving the presentation of my paper 924 for this conference, and thanks to all.